Hi everyone, and welcome to today's session on Bayesian neural networks. So far we've looked at the definitions of aleatoric and epistemic uncertainty and saw that there are some issues when differentiating between those two. However, there are still applications where it might be worth to be able to differentiate between aleatoric uncertainty, which is the uncertainty that comes from an inherent randomness in the process, versus the epistemic uncertainty, which comes from a lack of knowledge. Okay, and one way to do this are Bayesian neural networks. And so far, we're just gonna look how Bayesian neural networks are different from standard neural networks. So a standard neural network, let me get my pointer here, can look like that. You basically have your nodes that are connected. Here at the very beginning, you start with an input. Your input can be basically anything. It can be just your tabular data, so the variables, but it can also be a text that is tokenized, which basically means that you just split the words in like sub-characters and feed that to the neural network. Or for example, if you work with images, image is just like a collection of pixels, and every pixel has a certain color that can just be described by the amount of red, green, and blue there is in the pixel. And these are all possibilities how you can basically map any kind of input into numbers, and those numbers can be fed through the neural network. And then a neural network is just basically a mathematical calculation where you put here your inputs in. You multiply them with the weights. You have certain nonlinear activation functions that are used so you can also describe nonlinear relationships. And basically you do that for a lot of hidden layers until you then combine all of that into a single output, for example, for a regression case. Or you can have, for example, in a three-way classification, you can have three output nodes here in the end. I mean, obviously nowadays, the real neural networks that are used in, for example, large language models have a lot of different layers in between, but for now, for us, it's enough to understand them like that. Okay, and for a standard neural network, it's important to understand that it learns one set of weights. Those weights are all the weights between all the connections. And since you just have like a fixed scalar value for each of the weights, so each weight just is a certain number, for example, minus 0.73, and if you multiply all that, you get one single output, one single point prediction. And as you might see, there is not much information about the uncertainty in a standard neural network. Bayesian neural networks try to improve that problem by, instead of just having like one fixed weight, they basically learn a distribution over the weights. And since you have, instead of a fixed value everywhere, you get all the connections here everywhere are distributions. Your end output is then a distribution as well. And the good thing about that is that we don't just have the point prediction, but we also have information about the spread of the prediction. So if it is very peaked, for example, we can be very certain about the output, whereas if it's like, for example, a very broad distribution that is predicted as an output, we know the uncertainty is higher there. Okay. Now we're going to look at a little bit of math. They are called Bayesian neural networks because there is the Bayes rule. Thomas Bayes was an important statistician that basically introduced the idea to describe certain relationships with full distributions instead of single values. And like Bayesian statistics is basically a counterpart to frequentist statistics, but actually that's not too important. It's just interesting for me as a statistician to tell you a little bit about the roots of all that. And Bayes rule, you've probably heard about at least the basic Bayes rule in your Statistics 101 course. If we here describe it in the context of Bayesian neural networks, it looks like that. We are interested in the posterior distribution, so we want to know the probability, this distribution of our weights, W, given our training data, D. And to get this posterior distribution, what we do is we multiply the likelihood. So how likely is it to observe the data that we have given a certain parameter set W times the prior distribution over the weights. And since we want to have a properly probability distribution here, we need to normalize it by the evidence. This is basically the probability to observe all of the data. And this is basically the difficult part, because this is basically like a very big integral that's very difficult to compute. And this is what makes all this Bayesian stuff a little bit more complicated, because if you see that obviously it has the advantages that it can give you proper information about the distributions, which is oftentimes very, very useful. But this is the reason why it's more difficult than like classical frequentist approaches, like just maximizing the likelihood. And yeah, that's basically the reason that it gives you something, but it's also more expensive and more difficult to do so. And we will look in the next video on how to do inference then specifically. We are funded by the Deutsche Forschungsgemeinschaft and our copyright. Thank you and bye everyone.